Algebra 2, Section 5-6, Radical Expressions. So vocabulary for this is going to be pretty important. We have a concept here called rationalizing denominators. And basically, if you have a fraction with a denominator that's a radical, you need to figure out a way to make this a non-radical number or a rational number as opposed to an irrational. And the process of doing that requires multiplying the top and bottom of your fraction by a radical that'll undo the radicalness. So in this case, 2. If I multiply the top and bottom by square root of 2, I end up with the numerator of 2 root 2 over root 2 times root 2 is square root of 4, and there it is, no longer a radical. We get a 2 in the denominator. By the way, since this 2 here is being multiplied to this root 2, and you've got a 2 chilling out here, you can actually cancel them. So this thing becomes simply the square root of 2. So rationalizing the denominator is that process of fixing the denominator so it's a rational number. When we talk about like radical expressions, it's just like having like terms. So you remember we would have something like 2x plus y plus 3 minus 5x. And hopefully you would recognize that 2x and 5x are like terms because they have the same variable, right? We would have like radical expressions, all right? So like radical expressions would be like 2 root 3 plus 5 root 2 plus 3 minus 5 root 3. What I'd like you to know is that if you have the same radical, you are if they have the same radical, they're like radical expressions. So we can join those terms together. Just as 2x and minus 5x can come together to be simplified to be a negative 3x, 2 root 3 plus minus 5 root 3 can come together and give me, when I bring them together, a minus 3 root 3, and everything else would stay the same. So all of these guys would just have to remain exactly as it is. Finally, the concept of conjugates really comes into play when we're rationalizing denominators that are not simple radicals but radical expressions. For instance, if I had a fraction that had, let's say, a 2 in the numerator but a square root of 3 plus 5 in the denominator, here this is a radical expression. It's an expression that involves a radical. And to rationalize the denominator, it's not going to work if I multiply the top and bottom by root 3 because I'd end up with 2 root 3, and down in the denominator I'd have to do the distributive property, and you would see that I would end up with 3, that's root 3 times root 3, plus 5 root 3, another radical expression. Not helpful. So when we get to some examples, what you'll see is that in order to do these types of problems, you're going to have to multiply by the conjugate version of the denominator, a 1 created from the conjugate version of the denominator. So this, believe it or not, multiplying the top and bottom by square root of 3, changing the symbol, minus 5, right? So I change addition to subtraction, and if this were subtraction, I change subtraction to addition. Changing that simple thing will give us the opportunity to, we would rock a FOIL method here, and end up with a rational number in the denominator. So without further ado, we're going to go ahead and scroll down and take a look briefly at this key concept. Basically what we know here is that if you have a situation where you're taking the square root or nth root of any number, so let's say I was taking the square root of a number like 40. What this tells me is that I can look at this as the square root of 40 times square root of 4 times the square root of 10, and that's equivalent to the square root of 4 times the square root of 10. And honestly, being able to do this gives me the opportunity to simplify the square root of 40 into square root of 4 is 2, and the square root of 10 can't be done. And I can say that this is equal to this. So our first example here lets me know that I can look at this as this. I can look at the square root of 16p to the 8th times q to the 7th broken down in this way. I can take the square root of 16, which is 4. I can take the square root of p to the eighth. What times what gives me p to the eighth? That would be p to the fourth power. And then over here, q to the seventh power. Well, when I look at this guy, I know that this can be broken down into q to the sixth times q. And when I think about that, I know I can take the square root of that, which is going to be q to the third. But I can't take the square root of q. That stays underneath the radical. And that's how I'd simplify that problem. When you have to simplify quotients, it really does mean, and it doesn't say this here, but the expectation is that you're going to rationalize the denominator. So here as I look at this problem, I can simplify it as best I can. And when I do that, I'm going to get square root of x to the fourth power is x to the second. Square root of y to the fifth power is going to be y squared times the square root of y, because 1y doesn't actually get free if you think about it that way. But this square root of y in the denominator is a problem. And the problem is we've got a radical in the denominator, which traditionally mathematicians don't like. So we're going to multiply by a gourmet 1. And what I mean by that is a specific 1 for this situation. You know, when we multiply by 1, we're not changing the value of the problem. In this case, by choosing a 1 like this, I'm going to get to change the look of the problem. What I want to do is change this radical situation. So I know if I multiply the square root of y times the square root of y, I'll just get a plain y, which is what I want. So the numerator is x squared times the square root of y. That's not going to change. But the denominator is going to be y squared times the square root of y times the square root of y, which is just y squared times y, which eventually just gives me the y to the third power. The numerator stays the same. Let's look at part B. Here we're asked to take the fifth root of 5 over 4a. What I would do is break this guy down, recognize that I'm talking about the fifth root of 5 over the fifth root of, peep game, I'm going to write this 4a as 2 squared a. Breaking it down into its primary or prime number factorization really is helpful, and you'll see why. I need to make sure I multiply this guy by something that I can take the fifth root of eventually. So I'm looking for this gourmet 1. I'm going to have to multiply it by a fifth root of something. And whatever it is I multiply it by, I need to make sure I can take the fifth root of whatever I end up having. I already have 2 2's here. So if I had 3 more 2's, 2 to the third power, I would end up with 5 2's. That's excellent for me because I can take the fifth root of 2 to the fifth. Similarly with this a, I'm going to rock an a to the fourth power because a to the first and an a to the fourth will altogether give me a to the fifth, and therefore I can take the fifth root of a to the fifth. The numerator up here has to look like the denominator in order for us to simply be multiplying by the number 1. So at this point, the denominator becomes the square root of, the fifth root rather, of, the fifth root of 2 to the fifth times a to the fifth, which simplifies beautifully as 2a, and the numerator, well, now everything being multiplied will be under the fifth root radical. So I've got the fifth root of 5 times 8, that's 2 to the third, times a to the fourth. And so that's going to end up being the fifth root of 40 a to the fourth. Since there's no perfect fifth or perfect number to the fifth power that resides in 40, this will be our final answer. Here in example 3, it really does make sense again to prime factorize, so I can rewrite the problem like this. Now I'm going to take everything and multiply what's underneath the radical with what's underneath the radical, and then the whole number with the whole number. So 6 times 3 is going to give me 18. Then I'm going to get the third root of all the other stuff. 3 to the second times another 3 is 3 to the third. 2 to the second, or actually 2 to the third is going to come right here, and n to the second times n is n to the third. I can indeed take the third root of each of these. So I'm left with 18, whole number, third root of 3 times 3, third root of 2 to the third times 2, and then third root of n to the third times n. I think I said third root of 3. I really meant third root of 3 to the third power. So after I get this, I end up multiplying all of it together to get 108n as my final answer. So now let's check out example 4. Here in example 4, we're going to add and subtract radicals. Notice that all of these radicals look radically different, right? So the square root of 12, the square root of 27, the square root of 48. The first thing you want to do is simplify the radical as best you can to see if perhaps you have like radical terms. So this is a very simple way of breaking it down, making sure that each radical is divided into at least a perfect square, because I'm talking about square roots. When I do that, I end up with 2 times 2, the 2 coming from the square root of 4, leaving me with the square root of 3, and then 3 times 3 coming from that square root of 9 times the square root of 3 plus 4 coming from that square root of 16 times the square root of 3. So finally, I end up with 4 root 3 minus 9 root 3 plus 4 root 3. Since all of these have that root 3, they're like terms. They didn't look like they were like terms, but once I simplified it, I saw that we did have like radicals. So now I can join these together as if it were 4x minus 9x plus 4x. So I'm going to join them all together, and I'm going to end up with 4 minus 9 is going to give me a negative 5. Negative 5 plus 4 is going to give me a negative 1. I'm going to end up with negative 1 root 3, which I can actually write as negative root 3. In example 5, when we're multiplying radicals, we're basically using the FOIL method. So if you remember, I don't like to call it FOIL method, I like to call it the extended distributive property. I'm going to take one term and multiply it by the other two terms in parentheses, then take the next term and multiply them exactly like that. So here's what happens. This times that is going to end up giving me 6 root 5. And then 3 root 5 times this guy, root 3, is going to end up giving me a positive 3 root 15. Now let's go for the blue. Negative 2 root 3 times 2 is going to give me a minus 4 root 3. And then negative 2 root 3 times root 3 is going to end up giving me this minus 6 here. And how did we get that? Well, 2 times root 3, this negative 2 times root 3 times another root 3 will end up being negative 2 times 3, which gives me a negative 6. And now what I'm going to do is see if there's any like terms to join together. Root 15 here and root 5 and root 3, these are all different radicals, so this is the best we can do. We've got to stop here. Let's FOIL method this guy. So 5 root 3 times 5 root 3 is going to end up being 25 times 3, which is 75. 5 root 3 times 6 is going to end up being a plus 30 root 3. Then we have a negative 6 times 5 root 3, and we'll get a negative 30 root 3. And then finally, when we multiply minus 6 times a positive 6, we're going to end up getting a negative 36. I want you to take a look at something here. Notice how this radical term, these two radical terms look exactly the same, except one's a plus and one's a minus. Look at what happens when we multiply them together. We realize that this term ends up going away and this term ends up going away. And when this happens, we end up with 75 minus 36, which ends up being 39 as my final answer. Notice 39 is what kind of a number? Is a rational number. And so we have rationalized this in a sense. This number comes out as rational, and we realize that these guys are actually considered conjugates. So that's the beauty of conjugate pairs. Using that concept here, we're going to multiply the top and bottom by 5 minus root 3 over 5 minus root 3. And we're going to FOIL it. So after FOILing the numerator, I end up with this. And FOILing the denominator, the center term goes away. I end up with 5 squared minus 3, which is 22. And then I end up with, in the numerator, 8 minus 6 root 3. Recognizing I can factor 2 out of each of them, I did. And here's our final answer. And here are some suggested problems.